Yes, sir. You are audible, sir.
Yes, sir.
So any queries before to start our the second session? Any queries or any doubts?
Sir, shall we wait for 2 more minutes, sir? Yes, please. questions, sir. Participants will join meanwhile.
So, good afternoon, participants and faculty members.
Good afternoon, sir.
Good afternoon, sir.
Dear participants, let's start the second session. So over to you, sir.
Yes, ma'am. Thank you. Uh, Hopefully, you people had a good lunch in the afternoon. And this afternoon session, surely it won't be boring and it won't be too much heavy to our discussion. So in the morning, we have went through with what is basics of fog computing model and what is open reference model and a small case study of airport security system we have gone through. So with reference to our open reference consortium, they have brought different kind of case studies models that to help different developers, manufacturers, and industry peoples to bring different kinds of IoT devices and folk devices in the market. So as per the survey reports that we have received from Statistica 2020, it has been reported that nearly there will be 50 millions of devices, IoT devices will be upload in the functioning of the IoT industries nowadays by this 2020. And it has been expected another 25 percentage of increase in the IoT devices by 2030. So referring to this information, the growth of this IoT devices and folk devices in the market is very huge, and it is expecting good demands of different tools and different engineers and different research teams and companies in the market. So this fork and this edge model, surely it will be giving a good kind of and a good number of opportunities in the market. So here, this in this afternoon session, we'll be discussing two different data sets about your fork computing model. One is ecosystem. We'll be just referring to what are the different kind of ecosystems is available in the market. With referring your fork computing ideas behind. And the second one that we are going to discuss is how there's SDN, the next generation SDN is giving hands to this fork computing model. So before getting into this, I'll be just giving a small brief what this industry 4.0 revolution is. So we might have experienced different kinds of industry development in our experience. There is a industry 1.0, there is a industry 2.0, 3.0, and we are in the place of industry 4.0. So this industry 4.0 is very well referring to the development of intelligence devices in the industry spectrum. So the development, production, and support of different kind of intelligence systems is in the market. So hopefully we are also experiencing our mobile phones are nowadays giving different kind of features, different kinds of, so which meets the people's and customer demands nowadays. So our mobile phones are added with GPS service and cloud computing facilities. This fork model is also referring our mobile phones can also be a part of this fork computing environment. So the intelligence can be added with your mobile phones, your laptops, can also bring this fork computing, giving more support to the development of customer needs. So we might be hearing smart cars, smart agriculture, smart lights, and smart devices of different in titles. So we are hearing so much of development with the title of smartness. So along with this industry 4.0, our artificial intelligence, machine learning, and data mining, all these ideas also coming into the play. By the way, the development of different industry roles are more in numbers, maybe. So in upcoming years, we may be seeing more number of IoT devices in the market. So as I told you in the morning example, the surveillance cameras nowadays are coming with a support of fork models. So which is somehow the bandwidth utilization and the latency issues and the voluminous that we are communicating in the network, the transportation issues, all this could be reduced, somehow reduced and handled by your fork systems, right? So we'll be getting into what is this Industry 4.0 is. As I told you, this Industry 4.0 is a revolution which is making the manufacturing industries and production industries and different, even healthcare industries, as automobile industries, is bringing more intelligence devices in the market. By the way of bringing all these ideas is, the thing is, the industry is getting benefited with the continue business supports us business expansion and better quality of product and better personalized products is for customer needs is all this could be given by your industry 4.0. So this session will be discussing about the idea behind what this eco model is, the ecosystems is, will be a brief of what is Industry 4.0 will see. And the benefits of fog computing with IoT we will be discussing. And a few different of smart devices, say smart lighting, smart energy, smart agriculture, and smart transportation, and all this we are going to see, and we'll be seeing how your fork model is supporting to enhance the quality of these devices. So these devices are not limited to, but we can have a visit of how this fork model is giving us support for these devices. And finally, we'll be discussing what are the future scope of the fork model for this smart devices or ecosystem. Right. So I just request our audience to just look at this the image that is shown in your page. It is the automation pyramid of Industry 4.0 information. So if you look at this, the Industry 4.0, which is taking a layover, the sensors and actuators and systems and internal services, connectivity, network service and ecosystem, right? So all this will be bringing industrial transformation, which will be enhancing the services, platforms and application exchanges of ecosystems with our vision and the innovation and the leadership. So here, this Industry 4.0 is supporting, urging to bring the devices which is capable of intelligent computing or intelligent supporting of the customer needs and demands. So here, the introduction of this IoT devices in this Industry 4.0 and this fog environment. The IoT systems are powered enough in the last couple of years, and the lag of the things that we identified from the cloud computing, say that the bandwidth allocation, utilization, all this has been resolved, all this has been limited, all this has been controlled in a better manner. By having this cloud-based devices in the IoT platform, so there are few limitations we are facing in. So the subscription-based cloud support, unused silicon power in the edge devices, huge amount of raw data communication in the cloud, resulting the higher latency and the dependent of internet connections and overutilization of network bandwidth. All these are the limitations and the difficulty of your cloud-based IoT environment. So this folk systems are giving a hand, and the things as which we are referred as the difficulties or the lagness or the drawbacks are getting resolved by having these IoT devices in this place. So here this folk computings are leveraging the IoT solutions that it can control, manage, administer the local devices without the external dependencies of your cloud-based services. By the way, that devices not necessarily be subscription-based cloud services that to take up the data and take up the process in the cloud environment. And moreover, beyond this cloud subscription and the communication, so the global distribution of the network, so the folk computing is empowering your edge nodes, gateways. This could utilize this distributed network power and its support, which could make this local decision with devices, edge devices. And this can be the temporary storage for the analysis of your data sets, which is given by your IoT devices. So this kind of a distribution of work and distribution of computing power and distribution of data. So this will make the limitations is by your cloud computing could be resolved, and this could be solved. So having this fog and the IoT devices, so there are a huge number of benefits. So the very first benefit we can represent is that better bandwidth utilization. So this is what the bigger worries is that the cloud computing is having on. So better utilization of a bandwidth, unnecessary pushing of data reduction, all this could make your the bandwidth utilization in a better way. And real-time operations with low latency, which is obvious and it is very much demanded nowadays. So the folk computing fabricates the data sets based on its criticality, based on the needs, based on the type of a data, based on the nature of a data. The folk is having the capacity of classifying your data sets, and according to this could give it the computing power, giving decision-making power. All this could very much reduce your latency time. And further, this folk also focus more on optimal use of your edge nodes. So as we are discussed in the morning, the folk nodes are having the capacity of knowing or communicating with your neighbor nodes participating in the folk communication. So in which, so these devices which are designed maximally are leveraging the edge node resources to overcome the limitation of overcloud computing, so which is not necessary obviously, and the optimum usage of a network bandwidth, so that is very much required. All this could be given by your folk model, right? So the first one example that we are going to see, check about your ecosystem is the smart lighting, which could be given by your folk model. So I hope you people may be hearing and experiencing this smart lighting technologies nowadays. There are so much of our devices and models is available for the smart lighting technology. So this lighting industries are undergone a bigger revolution and transition from wired interfaces to wireless interfaces. So we might have experienced in early days is the lights and bulbs are usually wired, and there won't be any capacity further. You don't have any support of computing or storing or communication. So the bulbs and lighting devices are just emitting lights. But this smart lighting technology, which is added with your folk, is empowering this nodes, enabling smart lighting with a complete independency with cloud providers. So the OEMs, the manufacturer of your different devices could develop, prepare different kind of a smart lighting technologies to the market and for the customer needs. So this folk computing enable lighting solutions which enabling which enabling these manufacturers with, so they can have a local control, monitoring, and management capacity to this end devices. So the devices could monitor and manage by themselves, or this could manage the neighbor devices, neighbor lights in the nodes. And using localization features along with the data of the statistical information, say that the sunset information or a sunrise information. So the customer, the end user would be given with the option of scheduling the lights on and off facilities. Even the motion sensors and motion detectors, this could added with the smart lighting technologies, which could make the lightings supported whenever it is necessary on. So this can be further expanded in a global reach, and this could be with remote areas too. And this devices can also be capable of preparing the reports of energy consumption per device, or maybe in a group of devices. So the smart lighting technologies is not only just giving a lights also, but it is added with a capacity of the scheduling and communication capacities and the coordination capacities with the neighbor devices, which could make this the smart lighting technologies could help the end users very uh, uh, interesting and happily, right? And the second technology which is comes with this smart energy system. So we might be here that what is energy system is all about. So energy systems normally different kinds of energy systems are available in the industry platforms. So this could be the energy generators. This could be the solar farms. This could be wind farms. This could be water farms, gas distribution networks. All this could. So here, when we are bringing this folk model into this, so this OEMs of this smart energy device manufacturers, so they can have a capacity of, they can give a real-time fault detection with a low latency of the reactions. So the devices are capable to fault detections and real-time responses, so that the energy generation, energy management industry could handle the things is very easier. So each node in the edge networking, which could be data enabled with a data analytics capacity, so that it knows it how much the energy is it's generating and what its capacity is and how this it could be. So all this data analytics capacity is also added with this edge devices. And geo-distributed networks is which allowing the pinpointing of fault regions in case of any difficulties or faults as identified with the devices. This could be easily identified in our folk model, which could help this industry manufacturers can easily identify and support the devices with less downtime of the devices. And further, demand analysis with MTM interactions. So this could also be given by our smart energy technology along with this folk models. So on-demand based automatic distribution of switches and other supporting needs, all this could be given by your smart energy technology along with your folk model. And further, the other model is your smart agriculture. So this folk model also giving a support for your agriculture platforms too. So here this IoT enabled devices, smart agriculture is giving a nice and better enhancement in their fields. So farmers are moving forward to have a different kinds of sensors which are very much necessary for their yielding. So the temperature sensor, humidity sensor, motion sensor, ambient light sensor, all the sensors could also be connected with a smart agricultural environment, so that the farmers who needs this different kinds of data that to maintain their carts and the farm fields, so they can nicely use all these devices along with folk support. So the systems could be automatically maintained by your folk nodes. Say that the temperature sensor is alarming something, or a humidity sensor is alarming something. So the necessary actions could be initiated by your folk nodes by itself. So that the drone technologies which is also there in the market. So the drone technologies can also be used along with this IoT, where this drones can also support this farm fields for different needs of the smart agriculture. And further, the capacity is further enhanced so that localization features and can predicting the ideal harvesting time. All this is possible when fog and IoT is joins their hands. And expanding the global reach of most remote rural areas is without internet connectivity is also possible when a cloud is take a place and take a part of the services. And generating crop health analysis. So this could also be given by your smart agriculture so that the farmer may know it, how much the yield they can get from this acres of the fields, and everything can be analyzed, everything can be maybe predicted well advanced in the farming field. So live stock marketing, health analysis, and location tracking, all this is possible when we bring this folk along with this smart agriculture model. And smart transportation. So as this things are possible, so lightings is possible, then agriculture is possible, right? So if all this is energy systems also, all this is possible, so transportation system. So this transportation system also enhanced and improved further by having this fog computing empowered with different supports and capabilities, right? Here it is providing interflow communications over distributed networks. So in a smart transportation model, so the communication between different nodes which could inform the transport information of different devices, different vehicles in the real ground. This could be communicated, this could be analyzed. Even we have models here, the data analytics model, which could analyze transport information and traffic information from mapping systems also. So this could further extend, right? So the inter-flow communication in a smart transportation solution, which gives a better real-time traffic analysis information to the customers, maybe for the travelers. So street light control and time and weather control, this can also be possible when the smart transportation system along with this IoT model. And real-time traffic reports, suggestions for alternative routes, and inter-vehicle communications in cars, smart cars, all these are possible when we go with fog and IoT connected with. So these are all the different examples we have just visited. As I told you, there are different smart devices are possible nowadays. So not only with these four smart devices we are listed here. So beyond this, the healthcare industry is also doing, and the manufacturing industry is also doing, and the devices which are participating. So this electronics industry, say your sensors, actuators, right? So the kinds of different sensors. So these are all the elements is participating at the edge level of your fog computing. So how this fog model can suggest and recommends the capacity of computing power, storage power, and communication power with these elements is, which will make more smart devices coming in the market. So this was a small brief of what are the different ecosystems that fog model is having with. So as we said, the hybrid computing models, right, which could bring real-time analysis of data and the information that we share with, right? So this could make your fog computing further enhanced with. And the future of the fog computing, so which need to be further enhanced with adding more capacities, adding more computing power, and avoiding the bottlenecks of computing. So this will make more devices coming in the market, right? This was a small brief what your ecosystems is and your fog joining together. Right? So any queries in the space? Any queries? Shall I continue further?
Yes, sir. Continue, sir.
So the next one that we are going to see is what is that the next generation SDN and fog computing is. First, we get into what is that SDN technologies. And if you know what is that SDN technology, then further how this could be improved with next generation SDN. Right? So this was the agenda of this topic discussion. So the things is that we are going to see is this, the introduction of what is fog computing along with how a SDN is coming with, and the small brief what that fog computing is giving a support for enhancing this SDN model, and some examples of SDN model and how this SDN is transforming itself to bring the needs of industry nowadays. That's what the agenda is, what we are going to see. So here we just start with the cloud computing has been turned into a bigger revolution along with this computer science and engineering, and essential for all these modern communications. So we agree on. So without this, the transformation and revolution and the support of this, we could not make bigger modern communications nowadays in the network. So here, this advancement, this enhancement are bringing different kinds of approaches and different kinds of architecture into system development. So this might be your distributed computing and mobile edge computing, fog computing, and cloudlets. So this has been brought new ideas and new mechanisms of processing a volume of data and bringing computation closer to our client devices. So here, along with this software-defined networking, so has been gone into the evolution of bringing a full network programmability. So this is what the place where SDN is taking a part along with your fork. So the full network programmability is a capacity your nodes are going to bring this. And by the way, that fork computing is enhancing itself and bringing new devices in the market. So the requirements which are need by this edge-based data processing are addressed by your SDNs. So basically, edge devices are lightweight devices which are capable to bringing the computation facility or storage facility or a communication facility. But so how we could expand this? How do we program all these devices which can make your devices more supportive in the market, supportive in the communication, right? So fork already we've gone through and we have visited. So which provides the missing links between the needs of data to be pushed and the data to be analyzed in the edge. So this is what the basic information. And what is this software defined network is? So this is also an emerging technology. So this has been given to a new revolution nowadays. And basically this SDN is a technology which giving a support of bringing the computational facility to the edge devices. So here this SDN, which is bringing two kinds of control information, something client doesn't control and the data planes. So which are separated by two different titles as say control planes and the data planes. So this control plane is taking the responsibility of taking care of network operating systems and which having the role of managing your network orchestration. So this is very much required when you set up a cloud network or when you set up a IoT network. So most of these computations are done at the edge level so that this could be the special need of your network units so that it's participating there. So when we are referring to enabling the next generation of SDN, so there is a need of bringing new technologies and new way of approaching this SDN is required. SDN is required. So SDN is referring to bringing new technologies in a hardware as well as in a software side. So in a hardware side, this SDN is referring to programmable AICs and FPGA and smart NICs are all coming into the market. So by the way, the hardware devices are programmable and they are smart enough, which could meet the needs of different communication your devices want to do with. And the idea of a cloud mindset, so which is zero touch operation and containerization, which we are told in the pillars. So the devices which need to be containerization, which could make a zero touch operation, so that the device could be totally complete enough to handle the different cases of the need that by your different devices. So and further the leverages, so the data planes, control planes and network functionalities. So all these devices are enhancing the features, enhancing the capacities by the way that the SDN can bring a new different devices to the market. So SDN is, it's not just a standalone can bring any new capacity to the devices. So until this development in the hardware and the software has been given, so SDN cannot do anything there. So the development of new technologies are required in both sides is hardware and software. And the way of approaching the problem, the way of the capacity to the devices, these things are important when we want to bring this SDN with the next generation data sets, right? So here we'll see what is data plane is taking a part here. So I told you the control plane is very much specific to the operating system, very much specific to the software that is handling all this. And data plane, which is consisting different network devices, which is taking a part of the communication. So it could be of routers, it could be of switches, it could be of sensors, which is responsible for all kind of operation your that network need to take care of. And further, these devices are just carrying all this data, and there will be the control of every packet that's communicated by your network. And this could be rightly handled by the specific node which could do this computation, and all this could make your the capacity of new devices. So please look at this the image which has been shown. So it has been shown two different units is there, and there is a processor, right? So I hope you could understand, right? So pipeline match of action table, so packet forwarding in the pipelines. So when the data are going to be from different sensors and different units to the computing requirements and computing needs, so the devices need to be with the capacity of the computations, the devices which could be the capacity of which could handle the case and which could refer to how this communication could be made in the network. And then the P4 language. So the P4 language is coming, it's a part of this next generation SDN. So which is taking a bigger role there. So which is it's a domain specific language, and it is formally specified forwarding pipeline. So this P4 helped them to design a code which could make the devices which are participating here, the switches or a router, all this capable of handling the capacity of processing or data handling and all this. So here this P4 is helping to describe the protocols, so how the protocols could be designed for this, and the protocol headers and supporting lookup tables and the different actions that need to be carried out, and the counters that we use it in the communication. All this could be nicely describable by your P4 platform. And this can describe fast pipelines, which could be by your ASC and FPGA. And this could be supporting your smaller switch devices also. And this is good for programmable devices, programmable switches, as well as fixed functions too. So there are the devices which could be programmable devices, which could be for fixed functions too. So here this P4 is supporting to optimize your chip resources to the application needs and support for new protocols and fixed function devices, which defines that how we the communication and how we the control plane of the particular data at the node that we are giving with. So here the programmable or a fixed function pipeline. So here, which will define set how this could be configured and how this could be mapped to perform a particular responsibility of your unit. So P4 is playing a major role there, which could do the programming capacity to work, edge devices are the devices which is taking up in the communication. Right. And there is a protocol which is referred as a PISA. So the protocol independent switch architecture, which will help them to, which will help the programmers to develop a better methods which could make your devices more capable of doing the computations, doing the additions and the capacity. Here, the programmers which are capable can declare the headers which could extract the communication information, which could be passed and which could be communicated to the respective programmable matched action pipeline. So the data sets need to be forwarded to the respective units and modules, which could be nicely identified and exactly traced, and this could be communicated to the next level of your matching and action pipeline. So programmer defines the different tables and exact processing algorithm for the units or the devices which is required to be. And further, the programmers can declares how this output of the packet will look like and how the output could be carried to the next level of communication. This can also be possible when this P4 can either support for this programming. And compiling comes this way that, so here we are shown a small skeleton how this the compiling of a small logical pipeline in a PISA has been carried out. So here the layer 2 communication and here the IP4 and IP6 communication. So P4 compiler will allocate the necessary resources to support the pipeline devices. So as we said in the previous discussion, this programmable parser which could identify what are the communications or data packets the nodes want to share with, and this could be routed through the internet address table. Then it will be come across with address tables of IP4 and IP6, and there's access control list which will be identifying, tracing the kind of communication this the parser needs to and the devices need to. This could be rightly classified and extracted from the parser, and which could further communicate it to processing your device capacity, right? So here, this case for a fixed function chipsets is, so here the P4 is, as I said in the beginning, so there are two kinds of programmable and a fixed set of fixed function chipsets. So the devices which are a fixed set of functionalities is, so the P4 is tailor a particular apps or a particular role, which is very specific, which is specific to the task the hardware is going to perform with. So here the switches which maps that what a fixed function the device want to be performed with, and here the portability of data communication is very much referred here, right? So here why we are to use this P4, right? So P4 is having the capacity of explicit packet and pipeline definition, which could enable the deployment to the heterogeneous targets. So we might be knowing the different devices which are going to participate, not necessarily be same kind of devices or same kind of models that we are going to. So the pipeline definition which will enable the heterogeneous targets of different units is the same program can be used for both things. As we said, a fixed function or a programmable targets is both things we can do with. So the language is very clear and the semantic enable automated verification. So this P4 helps the development of better programming capacity to the surroundings, so that the devices could be betterly programmed. So here further this could be useful for testing your devices and analyzing the results with a program itself. So here, if you look at this, the image we are shown here, so the program is arranged in the order. So the different entries that we are shown here. So the parser, ingress, and deparser, and packet buffer and replication. Again, then the parser, ingress, and deparser, buffer queuing engine, all this will take a part of identifying your data communication that and packet headers is, and tracing the packets is, and referring to different classifications is, and according to the capacity of your devices could be brought there, right? So here, this is what the general architecture your SDN is referring to, and here there are 4 layers as we are given here: the data layer, control layer, management layer, and application layer. So the data layer, which is more focusing on preparing the data sets, which could be prepared from different devices which are participating in, and control layer, which is taking a part of communicating different control information with your devices which are participating, and the management layer, which will be taking the role of controlling the different devices which are managing the different devices and the participation, and the application layer, which will be giving the interaction between the neighbor nodes which are participating. So this 4 different layers which could give the complete and concrete communication and the management of your devices in the model. So here there's the top model on the top of your control layer, the application layer resides with. The communication between the control and application layer is performed through the northbound interfaces, so that it comes at the top. And these interfaces which the application access the network, which are collected and offer most of your SDNs, and that's where the benefits are coming into, right? So here, if we look at the challenges of SDN, SDN is finding struck with the security uses. So there are many access points and identify the cloud services. That's a place this SDN is tracking with. And the network connectivity, the devices able to connect with the network and connect with the computing resources. That's the place the SDN devices, SDN is finding a difficulty with. And then security. So as we said since in the morning, so SDN is taking care of the security of all the nodes as well as the SDN can also support to bring the security models with the different devices that we use with. So which will allows the creation of private virtual network that are overlaid on the physical network, providing the way to keep your IoT devices separate on the network, but the same way the complexity of traditional the private networks are somehow solved by your SDN method. And network connectivity. So network connectivity is a very basic requirement of your any devices that we are bringing into the model. So here the applications or devices. Obviously, the devices are very much time sensitive, and it is very much connectivity sensitive. So that this is most the priority of your any devices which is participating in this fork and this model. So here it makes a sense that computing near where the data is being used. So so the edge device or this fork. The data that we are generating, so that's a place we should have our computing power and computing capacity. So that this could make your devices more active and more response to the events that is happening with. So when we consider this IoT scenario for the autonomous car, or the things as we have said in the earlier discussion, say that your smart light or your smart agriculture or your smart transportation system. So the real-time data transmission to the immediate decision making becomes cleared by this SDN model. So this could help the development and design of your the models as well. So SDN is a good fit for keeping the network support close to the IoT fleet. So because it will not support, so it will not, the system will not permit to tolerate this jitter and latency that's happened in the network. So this is the reference model by this open fork. What would be the next generation SDN is. So just have a look of what are the devices and how the model is participating here. So if you refer this, in the next generation SDN is having 3 different layers. So in the bottom layer, this P4 runtime is taking a part, and the different kinds of the programming models which could help the system to add more capacity to our devices. So different, the capacity is very much required. So here GNOI, so that the network operation interface, this network management interface. So both the things is which will be taking care of that coordinating with those devices in the different layers, and SDN control service and configuration service, monitoring and telemetry service, admin and orchestration service. All this could make the control and management of your devices more rigid and robust. And further, the inventory, global orchestration, and OSS and BSS, which will helps that next generation SDN can make more IoT devices and fork devices in the market, which could solve, which could meet the common public needs in the IoT model. Right. So this was a summary of the discussion we had for SDN. So this is a new architecture which will allows us to retain the benefits of SDN and NFV. So the current existing SDN we are holding on, as well as this NFV also we are having on, along with this the next generation SDN, which talks about the add-on features of the capacity by your P4 and the changes that we bring in this control plane and the data plane, which will minimize us the challenges and cost and unpleasant things which is happening, which is there in the network model. So the goal of SDN is to further improve the network control, and by enabling different enterprise and service provider to respond quickly to changing the business requirements. And further, the change improves the network programmability, supports automation, and reduces the maintenance time and cost. Right. So, by the way, this is what the references that I've used for the complete presentation. So there are different forums and different the consortiums, even the open fork and the different consortium, they have a different a list of discussion and different list of resource models which will make your the fork and IoT model could further improve the availability of different devices in the market. So any queries or any doubts in this? Yes, sir, please.
Sir, good afternoon, sir.
Good afternoon, sir.
Sir, what is the any for SDN? Is it possible for us to define the switches and then routers with the help of the SDN? That's what I understood from your lecture.
Yes, sir. Obvious. That's the thing that SDN is bringing the capacity to the different devices. So presently, the devices which we are using are the devices are not capable for the computing power. This could not be for the storing power. So this SDN is bringing the new capacity to our devices, so that your switches can also do an additional jobs. We are not straight away referring that the switches is going to do a complete task. We are not going to mean that, but the switches can also do additional task of doing a decision making at the place. So it can do the classification of what the data is going to. So whenever the transaction is communication is taking place, the switches could also understand what the kind of data it is forwarding further. So the capacity of the devices we are enhancing through this SDN.
Sir, actually, in the morning discussion, you had mentioned about the data analytics also. So what I want to add to this is actually, is it possible to add the intelligence into this these switches and routers with the help of the SDN? Is it possible, sir?
Sir, intelligence is that I mean that intelligence is what kind of intelligence we are going to bring in. So is that the switches are required to analyze and process a complete data? Is it required? That the question we are to answer there. So here, if the switches are going to process all this, then there is a no need of further computing powered by the fork nodes there. So here, switches are going to be enhanced further so that it will be identifying what data to be forwarded further and what could be decided there itself. So that's the capacity we are going to bring to the devices.
So actually, this what I am thinking is SDN actually will be part of the fog nodes, or else it is an in addition to the
Sir,
fog nodes.
SDN is a model, sir. It's not the part of this devices. It's a model. And the model refers that this SDN could make your devices with a programmable. The devices could be programmable further. So SDN is just adding a new feature through a programming models. So SDN is not going to be part there. So SDN is giving the way to make your devices enhanced or programmable.
Okay, sir. Very nice. Thank you.
Audience,
Dear participants, if you have any queries, please proceed.
so I want to add one more point here. The space and scope of this fog and IoT is still having number of open problems. So the people who are looking for research-oriented ideas as research-oriented features, is there you can refer this open fog and fog models as for further scope and demands in the market. Fine now. Audience, any other queries? Any other doubts?
Thank you so much, sir, for such a wonderful session. Your presentation on open fork architecture and SDN architecture really helped a lot. I personally have learned a lot from that, sir. And the description on how fork computing can be coupled with IoT and smart agriculture and transportation. Really a wonderful session, sir. Thank you so much. Thank you so much for accepting our invitation and spending your valuable time with us, sir. Thank you so much.
Thank you, ma'am. Finally, it has been a great experience to me. First of all, I'll thank our coordinator, Dr. Sharda ma'am, for inviting me to be part of this FDP program. And the other one, our another co-coordinator, Mr. Dr. Momoti. Because of him, I am the part of this FDP program. So it is a great experience to me to share the folk ideas and folk models to this audience. And for that, my sincere thanks to our co-coordinators, Dr. Gauri Ganesh and Dr. Ruba Chandra, and all of the faculty members having listened my sessions. And thank you for one and all. So any queries, sirs, you can
Yeah.
write to me. You can write to me.
Participants, any queries?
So my email ID is here. If you have any queries or any doubts, very well, you can post your queries here. I hope there is no more queries now.
So participants, no more questions? If there are no more questions, sir, thank you very much for the session, sir.
Thank you, ma'am.
Sir, hello.
Yes, ma'am.
Sir, we look forward to interacting with you for our future sessions also, sir.
Sure, ma'am.
Thank you very much, sir.
Thank you, ma'am. Thank you so much.
Okay, sir. Yeah, have a good day, sir.
Thank you, ma'am. Thank you so much. Have a good day.
That's all for today. I hope to see you all with the same spirit tomorrow. Thank you. Have a nice day.